Hello, I'm going to be simulating 5 different cases today of fluid flow over a cylinder at varying Reynolds numbers. So first we're going to start by bringing over our fluid flow fluent, and we're going to begin with some geometry in the design modeler. And this first one I'm going to do, this is basically the rundown. On the left hand side, I'm going to be doing a Reynolds number of less than 1 for this first case, so I'll name it that. And we're going to start by sketching the cylinder true to the z-axis. It's just going to be a circle basically with one depth, and our units are going to be in meters. Make this 1 meter. Next, we're going to draw our boundary region. I'm going to make this a 50 by 50 meter box around our 1 meter cylinder. And then what we're going to do is go to concept, surface from sketch, and apply it just to the boundary. Oh, and then generate. And then you'll know you did it correct when it has the gray box, but not in the circle region. Alright, so that is done with the design aspect. Now we'll go to our mesh. Alright, so for our mesh, excuse me, we're going to first insert a mesh, or a method, sorry. Apply that, and we're going to make it not quadrilateral, we're going to make it the triangles, and generate that. You should have something similar to this. And then after that, we're going to insert a sizing. And we're going to do a edge selection on the cylinder, and we're going to make the element size 0.025 meters and generate that. After that, you'll see it's gotten really refined here. It has a nice meshing around the circle portion, but then as you can see these chunks get quite large, so we'll want to refine that somewhat as well. So after the edge sizing, we'll do a inflation actually around the circle again. So what we'll do is right click, insert a inflation, and we're going to click the face, apply that. Boundary is going to be the cylinder, apply that. And then we're going to do, instead of inflation option, we're going to change that to first layer thickness. And we're going to begin with the same 0.25. After that, the maximum layers will be 40, and our growth rate is going to be 2.5. So we'll generate that. Once that's generated, you'll see it comes very uniform and expands nicely out of the center. But again, this is all too large. So lastly, what we'll do is insert another sizing, but this time it is for the face. We'll change the element size to 0.5 and generate that. And then you have this nice thin meshing before it gets to the main cylinder where it refines even more, because this is the area that we're most concerned about. So that is it for the meshing. So we'll exit out of that, right click and update. After the updates, we'll open up the setup. We're going to do double precision and 4 solver processes. Alright, so to begin, we want to be pressure based, absolute, and steady. Our model is going to be not the K omega. We're going to do laminar. And then we can close that. The materials, we're going to open our fluid and edit our air. So to make the calculations nice and easy, I just used 1 for most everything I can. So 1 for the density, 1 for the viscosity, and then change create that. Now for this first demonstration with the Reynolds number of 0.1, we're going to have a constant of 1 meter for the diameter, 1 for the density, 1 for the viscosity, and then our velocity is going to be 0.1. So after the material, go to our boundary conditions. Oh, completely forgot. Go back to your boundary and open up the mesh. Forgot to name each boundary. Not a problem. Click on the edge selection and we're going to name this the velocity inlet, outlet, symmetry, and we'll just name that wall. Now we have all of our names here. We can exit out of that, update our mesh. Go to our setup. Let me update this as well. Refresh. There we go. Okay, so let me double check that these are correct still. Yep, 1 and 1. Close that. Now boundary conditions. Like I said, we're going to make the velocity 0.1, and that'll be equal to the Reynolds number of 0.1. Apply that. And then we'll go to our reference values. We're going to be computing from the velocity inlet, and you want to make sure that these values are the same. And again, just because I made it very simple by using just 1, we won't have to worry about any calculations pretty much. And then our reference zone is going to be the body. Now, for this first example, I found that having the scheme set to simple made the post-processing reports and everything look better. So for this one only is simple for the scheme. That's the only thing we changed. And then report definitions, we're going to add our force. So we'll do new, drag force, we'll do drag coefficient and wall. Okay. And again, we'll do another one, but with the drag force on wall. Okay. Close. And you can see if those added by this here. You can name them if you want, but I'll just leave it the preset name. Alright. Next, we'll go to initialization. I do a hybrid initialization with 25 iterations just to make sure that it gets closer to machine epsilon. And then we'll go to our run calculation, and I do 500 iterations. And go ahead and calculate that. Oh, well, initialize and calculate. As you can see, it gets closer to the machine epsilon there. Now, since we added the force, dragger force report and the coefficient, you can see these here. This is the coefficient of drag and the drag forces on the wall. And you can also see the scaled residuals here. Excuse me. So we'll let that iterate, and then we'll pull up the post-processing. Actually, before we go to that, I'll go to reports, and you have to run the simulation first, then you go to reports, and you can click on forces, the wall, and print, and then it'll print it in the command window here for you. After that, we'll close this and go to our post-processing. Right. Now what we'll do is I like to add the vectors. It wasn't necessary for my project, however it gives you a good idea of how everything is flowing. So we'll do vector field. Location will be the symmetry 1, equally spaced. We'll do like 10,000. So you can see it's coming in, goes around, and basically very short velocity around it. And then we'll go to contour. We'll add a velocity contour first. I do 250 contours usually. And then you'll see for this particular Reynolds number, we expect it to be a nice symmetrical distribution basically. And then same thing with the pressure. We'll add that one, and it should give a similar result except for pressure, of course. As you can see, basically symmetrical. And then lastly, for our project, we needed to do a streamline. For the streamline, we'll start from symmetry, equally spaced, and we'll do about 10,000. This might take a second to load. And then there you have it. You can see a nice velocity flow around the cylinder. Now, for this particular case, I said that we used the simple method, because if you used coupled, I found that the velocity for some reason would, or the flow would come in and it would like tank to the right. So it would always give a weird result, and that's why I ended up just using the simple. It gave you a nice result, exactly what I was looking for. So I just ran with that. Alright, so that is basically done. So you can close out of that processor, close out of fluid for this particular one. And then now you basically did all the hard work, so we'll just right click and duplicate. don't know how to move this. Oh, there we go. Okay, see if you just drag it, I guess it's pretty simple. We'll rename this to the Reynolds number of 40. And since we already did the geometry, we don't need to do that again. And same with mesh. We'll go back to setup, open up the double precision on 4 solvers. Okay, we don't need to mess with any of the modeling stuff. We'll go to materials and the fluid. And for this one, we will be changing just the velocity again. So your density, viscosity is going to remain the same. So you just got to go to boundary layers, change the velocity inlet to 40 so that our Reynolds number calculates out to 40. Apply that. Reference value, make sure that it's computing from the inlet again, that all your values updated correctly from the surface body. And then if you wanted to run the reports, it'll already be in here actually because you did it on the first one. And then the initialization, you can see that it's still exactly the same. We'll initialize that and run the calculation. Oh, I might have messed up. I might need to change here actually. Let's stop that. Change the method to coupled for this one. And then initialize and calculate again. Super quick. Let's see the results. And then since we just duplicated it, it should carry over all of our results that we want to see as well. And there we have it. So zoom in. We'll see the flow separation occur right about here. And then we'll have some symmetrical circulating, recirculating wake in this region here. And then it'll kind of converge back together after a certain distance. So these are our streamlines. If we wanted to look, the vectors kind of gives you that same idea. We might need to add more just so you can see the recirculating. And then our velocity contour and pressure contour. All right, exit out of that one. And the fluent again. So we could duplicate this one, but since this is the one that uses the simple method, we'll just duplicate this one because we're going to use that from now on. Drag this over and open the setup. Actually, let's rename it real quick. So this one's going to be a Reynolds number between 100 and 200. For my case, I ended up using 150, just dead in the center. Okay, same thing, don't have to mess with the model, just need to change the settings on air and then the velocity. So for this one, since we're doing a little bit higher of a Reynolds number, I went ahead and changed the viscosity to 0.1, left the density alone, and then I went to my boundary conditions and change the velocity inlet to 15 so that it wasn't ridiculously high. although 150 meters a second wouldn't be ridiculous, but anyway. Compute from velocity inlet, make sure that your value is carried over, surface of the body. Again, your report definitions will be here, and you can see now since we copied the other one, the scheme is coupled for the method, and then initialize and calculate. Oh, it already loaded. I don't know why I was expecting it. Anyway, here's the streamlines. For this one, because it's between 100 and 200, the Reynolds number is 150. We're going to be looking for alternate vortex formation in the broad wake behind the cylinder, which you can kind of see here, and it's going to be offset. Let's see if I can increase the vector field to better demonstrate that. Maybe we'll do 15,000. Yeah, you can see this one's circulating clockwise, and this one's circulating counterclockwise. I can speak. And then, again, the streamlines. We'll see our velocity contour starting to get that turbulence as the Reynolds number is increasing, and pressure contour as well. Okay, now we'll be doing the 400 to 300,000, 3 times 10 to the 5th. For this particular one, I ended up doing 10,000. Didn't want to go ridiculously high, but fair amount above 400. Right, for this one, we'll go back to the air, and I did 0.001. Density remains the same. Boundary conditions, our velocity is going to increase to, actually decrease, but to 10. Close that. Go to our reference values. Make sure it all copies over correctly. And it's still the same. Initialize and calculate. Right. So this is our pressure contour, our velocity contour. We're going to see that it's going to have a very wide turbulent wake following the cylinder. Lots of mixing going on, and then our streamlines again kind of reiterates that there's a lot of mixing going on here. And lastly, our vector fields. Just vectors going everywhere. Oh, that's weird. I don't know if I hit a button. Might have. Excuse me. And then you can see the laminar separation beginning to happen basically on the top and the bottom of the cylinder as it flows overward. Better seen with the streamline. Right here and here. And that sums up the 10,000. And now for this one, oh, I forgot to name it. Go back real quick. So for this one, as you can see on the left, oh, actually I didn't even name that one either. That's funny. So the Reynolds number is going to be what? Greater than 300,000. So 3 times 10 to the 5th. And then for this one, I ended up picking a million. And so our viscosity is going to be 0.0001, so 4 zeros total, or 1 to the negative 5th, 5. And boundary conditions, we're going to change our velocity inlet to 10, which I think it actually is already. Yeah. Cool. Alright, simple as that, just run in and calculate again. We'll open this one. And for this one, what we'll see is the turbulent separation is a little bit further along. Instead of the top edge like it was on the first, or on that last one, it'll be a little bit further down. And the wake region is going to be thinner than the last one as well. So these are the streamlines. Here's our vectors, lots of mixing going on. Whoops. And then here's our velocity contour. And lastly, the pressure contour. So that basically sums up all of them. Like I said, the only one that you really have to do something different with is the method. For the first one, I ended up having to do simple just because the results looked a little bit better for my particular project that I was working on. And yeah, that basically sums up how the flow changes for each case depending on the Reynolds number. And then we also show how we can change the Reynolds number simply by altering one of the variables, viscosity or velocity mostly in this case. And thank you for watching.